This lesson is all about smart pointers, but I'll start off with a recap on the raw pointers, which are the pointers that we've been using so far in the course. Raw pointers are powerful because the programmer has full control. That is, the programmer has to manage the allocation and deallocation of the objects on the heap. While having the ability to manage memory directly can be powerful, it can also lead to all sorts of bugs and issues in our programs. We've come across these issues before, such as uninitialized, or in other words wild pointers, which are pointers that could point anywhere in memory. We can also have memory leaks, as we've discussed in previous lectures on shallow copying and deep copying, for example. If you recall, a memory leak happens when you don't allocate the object previously pointed at by the pointer. In some of the previous lectures I demonstrated that you can keep allocating new objects on the heap and then you assign the address of those objects to the pointer, right? That is, without allocating the object previously pointed at. So in that case you create a memory leak. We do not have an infinite amount of memory to run our program, so eventually we will run out of memory and the program will crash. We also have to deal with dangling pointers. A dangling pointer again is a pointer which stores the address of an object that has already been deallocated. Of course, you do not want to dereference an uninitialized or a dangling pointer. In programming languages such as C# and Java, something called a garbage collector manages the deallocation of objects that are no longer in use, or in other words that go out of scope. Now of course in C++ we as programmers have to do this manually, that is if we use raw pointers. Now if you think about what it means to manage something for a second, you may think in terms of object-oriented programming where one object manages another object, or in other words composition. We've also seen simple examples where some object can manage a pointer. At this point we already have an understanding of classes and template classes, and if you think about it for a second, it would be nice if we had template classes that can manage a pointer for us, so it can manage the allocation and deallocation of heap objects for us. In this example I have a template class called pointer manager, and in the constructor it's going to allocate a new object of type t on the heap. T again is the type parameter. And of course in the destructor it's going to deallocate that once more. The class pointer manager manages this pointer, okay, some pointer member which is a pointer to type of t. I'll scroll back to main, and this is what I mean now. We can instantiate that pointer, pointer1 is of type of that pointer manager, and now we can specify what type of pointer we want that object to manage for us, so integer for example. Now for this object to behave like a pointer, so in other words we can dereference it, and we can use the arrow member access operator on it. Those operators, again the dereferencing operator and the arrow member selection operator, would have to be overloaded. That is so that the programmer could work with the object in a familiar way, so as we would work with raw pointers. Taking this example one step further, I have an entity struct which is going to do cout entity destructor invoked. It has an integer member. I'll use that later on, and then getting back to the pointer manager template class. In the public section, I have an explicit constructor to avoid implicit conversions. The constructor has a formal parameter ptrp for pointer parameter, which is of type pointer to t, which again is that type argument, and that is a default argument which I set to null pointer. For this example I actually changed the name of the managed pointer here to m_ptr for member pointer, which again is a pointer to type of t. In the body of the constructor I'm going to assign the pointer parameter to the member pointer. I also have the destructor which is going to deallocate whatever member pointer points at. Also notice in the constructor we are not assigning anything on the heap in this instance. That's because we are going to do it where we instantiate the pointer manager, but I'll talk about that in a second. Then as I mentioned, for a familiar workflow you may want to overload the dereference operator and the arrow operator. Okay, so that's what I'm doing here. I'll go back to down here to main, and then I can instantiate pointer manager, and I'll talk about the entity here in a second. For the first example I'll just go with an int actually, and I'll just call it ptr1 for pointer1. Now as I mentioned, in the constructor we do not allocate an object on the heap now. Now what you can do is something like this. And while you can construct and initialize pointer managers in this way, I do not recommend it because it can lead to memory leaks. So instead what we are going to do is, you're going to declare the heap object within the initialization. What do I mean by that? Well, we construct pointer1 which is of this type, so pointer manager we pass an int for the type parameter t. Then we do new int and we initialize that to 44, so that is going to return an address which we are going to save, or basically pass in as an argument to this right here. And with that we are going to initialize the member pointer. The whole point with a pointer manager is ownership, and we want the instances or the objects to manage the pointers. Again, we want the objects to allocate and deallocate the objects on the heap. This is so that we don't actually have to work with raw pointers at all. And this is pointer 1, not just PTR. So I'm now using that overloaded dereferencing operator with the PTR object, which is a pointer manager. And with this declaration, the member pointer is now going to point to a heap object of type int, which will be initialized to 44. So we should get 44 printed out here. Build and run that, and you see that works fine, 44. And we can do this with our custom types as well. So I have this entity, if you remember, which has the destructor, and it's going to print out entity destructor invoked. This is where the arrow operator comes in. This overloaded arrow operator. This will work fine now. I can build and run. It prints out 55. It calls the entity destructor. So we get entity destructor invoked and then end of program. Now for the next example, and this is actually what I wanted to get to, is if I copy this. And let's say I want to create another pointer manager, pointer 2, as a copy of pointer 1. If you pause the video for a second, you can think what's going to happen when we build and run. Alright, I'll just build and run. And you'll see we get a crash. And that is because we are doing a shallow copy, not a deep copy. Now you can go and create a deep copy constructor, we've covered that before, and then also the deep copy assignment operator. But let's say that is not what we want. Let's say we want to prohibit this. Let's say we want to enforce unique ownership of the pointer that the pointer manager manages, and in that way each instance is responsible for managing its own pointer, and of course the object that is on the heap that its member pointer will point at. Well, in that case we can delete the copy constructor and the copy assignment operator. Let's just go and do that as a quick example. This will simply be a reference to a pointer manager constant. I don't have to pass it a handle because we are not going to use those in any way. And then I simply use the delete. And now I've explicitly deleted, or in other words prevented, the use of the copy constructor and the assignment operator. Now where we try and construct pointer 2 as a copy of pointer 1 using the copy constructor, we will get a deleted function error. Try and build and run that. We will get this error right here. Function was explicitly deleted. Similarly, I'll just remove this here. I'll just construct pointer 2 like this, and now of course the member pointer is going to be initialized to null pointer. But what if I want to assign pointer 1 to pointer 2 now? We will get that error again. Deleted function. Build and run, and you will see you will get that error again. And that is basically how we can create a unique pointer manager. So in other words, a pointer manager with exclusive or sole management of the pointer that it manages. Now in the next lecture we will actually discuss a smart pointer of that type called unique pointer. And thankfully we don't have to implement all of this functionality ourselves each time we want to use these types of managers. It exists already in the form of smart pointers in the standard library. And of course the implementation is going to be a bit different. We are not really concerned with the implementation. This was just a simple example. We just want to use the functionality, but I wanted to give you a basic idea. And then also the smart pointers will actually have member functions such as a get function to get the pointer as well, so that you can use it with all the code that does not support smart pointers. It will also have a member function to deallocate the object that is on the heap that the object's member pointer will point at, and various other member functions. But again, we are not really concerned with the implementation. This was just an example. We will be using the tried and tested smart pointer implementations instead, right, instead of our own implementations and trying to reinvent the wheel. Alright, what is a smart pointer? Well, a smart pointer is a template class that manages a raw pointer. In other words, it owns a raw pointer, and that ownership can be shared or not. That is, through copy constructors or assignment operators, for example, we can control whether or not we want to make that owned pointer available, maybe to other smart pointers. Because we have different smart pointers, we have smart pointers that sort of control the ownership in a way where they do not make the owned pointer available outside. And throughout this lesson we'll discuss the different types of smart pointers. And of course, since the smart pointer object owns, or in other words manages, the pointer, when that smart pointer object gets destroyed, it will deallocate the object on the heap through the pointer that it manages. So emphasize here that smart pointers are objects, alright, they are instantiated, they are not raw pointers. Because it can get confusing, smart pointer classes have member functions and overloaded operators. For example, we have member functions that allow us to deallocate or get the address or pointer of the managed heap object. Then we also have the overloaded dereference and arrow member selection operators, which allow the programmer to use the smart pointer object in a familiar way, right as with raw pointers. But again, it's important to note that these are not raw pointers, otherwise some of the syntax and stuff can be a bit weird, and when you see it in production code you might be thinking, why does this pointer have a member function all of a sudden? Another important note is we need to include the memory file which defines the smart pointers, so we need to include the memory file. Okay, these are the types of smart pointers that we'll discuss in this lesson. We have the unique pointer, the shared pointer, and the weak pointer. So a lot of this has to do with ownership, and we'll discuss this in more detail in the next lecture. As discussed, raw pointers can be the cause of all sorts of issues in our programs, and we can avoid that by using smart pointers and introducing ownership. And in that way, the owner that manages the raw pointers is responsible for allocation and deallocation of heap objects.